about the prerequisites. So as I told you, a first course in probability is basically the prerequisite for the course. But the level of the course, it's maybe not completely clear. So in case you want to read a little bit about the theory that you need to know, there are two main references. So let me just let me just verify. So this one here, so the theory that you need to know is in chapters 5 and 6, okay? And the second classical reference is, so this is, so this one is part of the Euclides collection, so it's available at the library downstairs. Hopefully it's not, it's available. And the second one is Barry James. And in Barry James, the required material is basically chapters 1 and 2. So in particular, I will assume that all of you know about the formal definition of probability spaces and random variables. Okay. So this is what I expect you to know. So now let's go back to what we were discussing yesterday. We were discussing about graphs. Okay. So we have some examples of graphs. Okay. So. So we had so the circle is the graph on which the set of vertices is the set of integers modulo n. Okay. So this is the one possible notation for the integers modulo n. And then we say that x is a neighbor of y if and only if let's put it in this way. The difference is equal to plus or minus 1. Okay? And here, this difference is modulo n. Okay? So this thing here will be, if I'm not mistaken, this graph here. Okay? So many times when the set of edges of our graph is understood from the context, we say simply, we call this guy a graph. Okay, so we say the graph, in this case, z modulo n. But of course, this is abuse of notation because this is only the set of vertices of the graph. Okay, so whenever the set of edges of the graph is understood from the context, we use we call the set of vertices a graph. Okay, so this is what was one example. A second example was the hypercube. So in the hypercube, what we have is this, and we say that x is a neighbor of y if and only if this is equal to 1. Okay? So these are binary sequence of length n, and this thing here is sometimes it's called the Hamming distance. Okay? Between two binary sequences. Okay, so when you look at binary sequences, it makes sense to call the distance between the two binary sequences the number of different entries of these two binary sequences. No? This is something very common in coding theory. So this is another way of defining the set of edges, no? Because we say that 2 points are neighbors if that the edge xy belongs to the set of edges of the graph. No? So this is the hypercube. Another one, which is very important, is the lattice. Okay? The lattice is an infinite graph. So the set of vertices is z to the d. Okay? So the set of vectors with d coordinates, on which each coordinate is an integer number. And here we take, we say that x is a neighbor of y if and only if the L1 norm of the difference is equal to 1. Okay? So in d equals 1, this is the lattice, no? This is just the the integer line, and d equals 2, what we have is something like this. Etc. No? And as you may imagine, I'm not going to draw the integer lattice in dimension 3. Of course, okay, so another example, which is maybe also very important, is what people call the periodic lattice. So what is the periodic lattice? In the periodic lattice, the set of vertices is Zd divided by nZd. Okay? So what does it mean? These are the integer vectors modulo d. Okay? So it's the same as the lattice, but modulo n. Okay? And then we say that x is neighbor of y if and only if this is not what I wanted to say. Okay, so the periodic lattice is just the lattice, but with periodic boundary conditions. Okay. So you see that in particular for d equals 1, the periodic lattice is the same as the circle. And also for n equals 1, n equals 1 or n equals 2? N equals 2. The periodic lattice is the same thing as the hypercube. You can check that. So all of these examples have a lot of symmetry. Right? They are very symmetric graphs, yes?
When you write down x, y, you mean that they are neighborhoods, right?
Yes.
Okay.
So all of these lattices here have a lot of symmetry. So this in fact, from the point of view of the geometry of these graphs, all points are equal. So if you stay at one point of these lattices, what you see around you is exactly the same, no matter which point you are. If you are in the circle, what you see is a circle. If you are at another point of the circle, what you see is exactly the same thing. Okay? So they are very symmetric, but usually when you are maybe doing some real-life applications of graphs, graphs are not like that. Okay? So these graphs are good in situations of which, let's say in more applied problems on which you do have symmetry, but in problems on which you don't have symmetry, those graphs are not a good idea.
Professor, então se a gente pega o exemplo, can you speak português, or do you prefer? Ok. Então a gente pega o exemplo de ontem, por exemplo, da plaza, seria ele está somente no boundary exterior, né, que seria o quadrado, que seria um periodic lattice, ou no anel interior, que seria aquele octágono, sei lá como é.
So, okay, maybe I will give one last example. Of these very symmetric graphs. So in the complete graph, V is just the set 1n, and all points are neighbors. Okay. So for n equals 4, this is the complete graph. N equals 5, what we have this, etc. Okay? So this is the complete graph. It's another very symmetric graph. And as I was telling you, these graphs are very homogeneous. So very symmetric. And the reason why we give these examples of graphs is because if you think a little about it, it's very difficult to actually write down a non-symmetric graph. How do you describe it? How do you describe a graph which is not nice? How do you write a formula for the edges of a complicated graph? It's complicated. So for example, imagine that so you have a database and you build a graph out of this database by some sort of relation. Okay, so for example, something that people use for a while, it was very popular to use this type of graph. It's you have cities in a country, and you draw an edge between these two cities if there is a flight between the cities. Okay, so that's a graph. And it's a very complicated graph. Okay, so it's difficult to describe. How do you describe it precisely? So, but okay, so, but from the mathematical point of view, you want to model, no, a complete, yes?
Não completo poderia ser grafo em que os números ímpares, eles têm duas conexões, os números pares só tem uma?
Mas,
todo x que o...
mas para onde que vão as conexões?
Tá, não fecha, ok.
So, but from the mathematical point of view, the question is different, okay? So what you want to say is, how do I model a non-homogeneous graph, okay? Because as I was telling you, in mathematics, what you usually do is that you take a complicated problem, you simplify it until you get a problem you can solve, and then when you solve that problem, you go back to the original problem and you see that whether the solution that you obtained in the simplification makes sense for the more complicated problem. Okay, so this is the philosophy of a model of modelization, no? And one way to construct a very irregular graph is something that is called a first attempt, no? Nowadays there are more complicated versions of this, but this was basically the first non-homogeneous graph that people define. It's called the Erdos-Renyi graph. So how does the Erdos-Renyi graph works? It's a random graph. Okay, so we take as a vertex set the numbers from 1 to n. Notice that whenever you are looking at a finite graph, you can always assume that the vertex set is like this, no? Because you just have to number the vertices. When graphs have some geometry, of course, this might not be convenient, no? For example, on the hypercube, in principle, I could have written here the vertex set as the numbers from 1 to 2 to the n. But this is clearly a very unpractical way to write down this set here. On the Erdos-Renyi graph, we start with that set of points, and then we take random variables which are indexed by the points on the vertex set. Notice that this index set here is exactly the set of edges on the complete graph. Right? So there is one random variable here. So these are going to be random variables. So let theta xe be IID. So this is the point at which I'm going to assume that you know about what I'm talking about, not about basic probability theory. It's that you need to know what does it mean IID, no? Independent and identically distributed random variables. With common law, Bernoulli with parameter p, with p between 0 and 1. That is the probability of these variables being equal to 0 is 1 minus p, and the probability of these random variables being equal to 1, it's equal to p. Okay? So these random variables are what? Are just coin flips with probability p. Yes? Independent and identically distributed. So these are just coin tosses with probability p. Now, Okay, let me write it differently. So we say that two vertices on a graph are neighbors if and only if the corresponding coin toss is equal to 1. Okay? So what does it mean? Yeah, so nowadays people don't have any coins anymore, so you cannot do coin, no, toss. But what people have nowadays is a cell phone, no. So you write here, you enter to some website. And you open a random generating number. True random number generator, powered by random.org. And then you do coin toss. Okay, so the idea is that for each one of the edges of the complete graph, we are going to toss a coin, and we are going to decide whether we are going to draw the edge or not. So I'm going to start. I'm going to do it. So okay, no, 0, 0. So very, very random. No, 0 again. 1, 0, 0, 1, 1, 0. Oh, well, not super fun. So something that you have to learn about randomness is that the human brain is super bad at detecting randomness. Okay, there is a story. This is a true story. So I think 2 years ago, I taught here at IMPA the course on measure theory. And you may have seen that IMPA has a very big library of videos of many courses. In particular, there are very good videos of the course in measure theory. So if you want to learn measure theory, you can watch the videos at IMPA. They are very good. So I arrived to the students and said, you know what? The thing is the following. So the course of measure theory is actually available on YouTube. It's not clear that I'm going to be able to give a better lecture. So what we're going to do is the following. So each day of the course, you have to watch the lecture beforehand. I arrive here, and I'm going to make I'm going to enter into random.org, and I'm going to select one student at random that has to go to the blackboard and explain what the video was about. Okay, so that's going to be the evaluation of the course. So so each day we select I select 2 or 3 students to explain about the different theorems, definitions, etc., on the corresponding video of measure theory. And I told them, okay, something very important about randomness. So the human brain doesn't understand randomness at all. It's very bad at that. In particular, you're super tempted to believe that if you are chosen one day, the next day you won't be chosen again. And what you don't know is that actually that is super likely. It's extremely likely that someone will be chosen a few times in a row. So that's what I said the first day. So the second day, the third day, and the fourth day, the same guy was selected. Fortunately, he was a good student, no? Because, but this is something that the human brain has difficult to recognize, no? Because the point is that the human brain is very good at finding patterns. And then when you have something which is completely random, what happens is that because if it is completely random, there is a very high probability of having some pattern. And the human brain will recognize it immediately, and it's going to discard it as random. Okay, so let's do it again, okay? So now I'm going to put, 6 points to have more things to do. So now we have an edge here, an edge here. This one is not there. An edge here, an edge here, an edge here. Now we go to the diagonals. This one is not there, not there. We go to the other diagonals. Not there, there, not there. Okay? So these are two different realizations of the Erdős-Rényi graph. There are theorems about the Erdős-Rényi graph. There's plenty of them because it's a super fun random graph. But the only thing that I wanted to show you is that these graphs are now highly inhomogeneous. Are very different, no? Whenever we toss the coins, they're going to look very different one to the other. Now, this one that doesn't have any loop, for example, or any closed circuit. This one has two closed circuits. Yeah? É a aresta.
Mas para ser grafo realmente aleatório, não deveria ser aleatório também a escolha do próximo vértice? Porque se você seguiu um certo padrão, não?
Sim. Então, não. A resposta é não. O resultado é o mesmo se eu fizer uma
Escolha aleatória de vértice e aresta.
Exatamente. Mas a princípio é uma pergunta legítima e a resposta é não, dá na mesma. Sim.
O nosso grafo, ele importa, por exemplo, digamos que eu vá naquele raiozinho, vai numerar eles em ordem como se fosse um relógio, 1, 2, 3, 4, 5. Se eu girasse ele para que cada vértice estivesse conectado a um mais, só pegasse e botasse levemente, ainda é o mesmo grafo? Ele tem o mesmo formato ou
Então,
a seleção dos vértices tem algum impacto?
Então, por exemplo, esse grafo aqui, a pergunta é a seguinte. Esse grafo aqui e esse grafo aqui são iguais? A resposta é sim. Tá bom? Porque o que eu fiz aqui no quadro é uma representação do grafo. São duas representações diferentes do mesmo grafo. O desenho não importa. Ou seja, na definição de grafo, na definição de grafo, não está escrito onde que os pontos estão no plano.
A não ser que sejam vértices nomeados, né? Os vértices foram-
Se os vértices forem nomeados, aí a coisa muda.
Mas mesmo que fosse nomeado, já não fosse 1, 2, 3, 4. 1, 2, 3, 4. Por exemplo, pode ser aqui no primeiro. 1, 2, 3, 4. E no último também pode ser 1, 2, 3, 4, entendeu?
Mas aí na definição de grafo são os mesmos conjuntos.
São os mesmos conjuntos. Eles só vai ser, sei lá,
Então, so different. So, for example, when I take two different realizations of this Erdős-Rényi graph and I draw the two graphs together, then I'm marking the vertices, and this is a different story. Okay. But for the moment, the only thing that I wanted to show is how to construct a graph which is no longer regular or homogeneous like the ones that we just constructed. But what is interesting about this graph, the Error-Renyi graph, is it is that it's still tractable mathematically. So you can still prove theorems and say meaningful things about it. And that somehow helps you to develop theory that will apply for more general graphs. So now let me make a definition. So So I'm going to introduce the concept of a degree. Of a vertex in the graph G. Okay, so the degree is the number of neighbors that a given vertex has. Okay, so I still have this one here. Yeah. No, that's the degree of a graph. Yeah, but this is the degree of a vertex.
Ah, okay.
Okay, so here I still have a picture. So you can see here that the degree, this an edge missing here, that the degree of each vertex here is equal to 4, right? So the degree is constant. In all these very regular graphs, the degrees are constant, no? For in the periodic lattice, no, you see that the degree here is always 2D, right? In particular, for t equal 2, the degree is 4. In the complete graph, so the degree is n minus 1, yeah? Não, depende. Se tem loop, aí tem que contar o x. So in the complete graph, we have n minus 1. So here in the Error-Renyi graph, well, it depends, no? So this is not homogeneous, no? Not all the vertices have the same degree, no? This one has degree 0, degree 1, degree 2, degree 2, degree 1. In this other one we drew here, so degree 2, degree 2, degree 3, degree 3, degree 2, degree 2. Yeah?
Is this also the case for directional graphs? So directional
depends on the author. No, it depends on your convenience. Sometimes you define the degree taking into account the direction. Sometimes you don't. It depends on the problem. So this is the degree of a point, okay? Notice that the degree might be infinite if the graph is infinite, okay? Sometimes people add a condition in the definition of a graph that the degree is finite, okay? This is something that people sometimes do. We are not assuming that the degree is always finite, okay? In the context of Markov chains, it's not necessary to assume that the degrees are finite, okay? So I'm not going to define the degree of the graph, okay? Because it's not a very useful concept in our context. But sometimes people define the degree of the graph G as the maximum among all these degrees. And sometimes they making this definition, what people say is that the graph has to have finite degree. Okay? So now let me go let me define what we understand by the symmetric random walk. Okay? This definition is not going to be rigorous for the moment. So the simple symmetric random walk on a graph, simple symmetric random walk on a graph G is a sequence so here is N0. So let me remind you, N0 by definition is the set of natural numbers that when you include 0. Okay? Yeah, so I think I told you about that. No, in the 20th century there was all the discussion about whether the 0 is a natural number or not, and the only outcome that discussion had is that we are no longer able to use the symbols n and n0 without explicitly saying what we are talking about. Okay. So for me, n0 is going to be the set of natural numbers including 0. And n without the 0 is a set of natural numbers not including 0. Okay? So these random vertices, how are they chosen? Okay, so it's a sequence of associations on which xn plus 1 is chosen uniformly at random among the neighbors of xn. Okay? So an observation, no, is that in order to this simple symmetric random walk to be well defined, we need to assume that the degree is finite for every vertex on the graph, okay? Because if the degree is infinite, how do you choose the next guy in this random walk? So if the degree is infinite, what does it mean to choose one neighbor uniformly at random? This is not well defined, okay? So
Mas quando você diz infinito, sempre numerado, é sempre discreto, né? Não vai
sim.
ascender.
Sim, sim. Isso sim está na definição de grafo. Tem que ser infinito enumerável. So this is a simple symmetric random walk. And on each one of these graphs, one can define the symmetric simple random walk. So let's see here, so in these two examples here, what happened with the simple symmetric random walk. Okay, so in this realization of the Erdős-Rényi graph, well, there are some things that may happen. No, you start here. The only way to go is here. Here you have two choices, no? Here or here. Here you have two choices, here or here. And here, if you start here, what happens is that you don't go anywhere. You get stuck there forever, no? So we need to assume something else, no? Okay? So, and you see also, I mean, this condition there, no? It's reasonable because a random walk that starts here and stays here forever is not the most interesting random process one can imagine, no?
Mas de fato não tem random walks começando aí, porque não tem um número do próprio vértice, então você não tem nenhum vizinho de X.
Não, começar poderia.
Teria o ponto do zero, né? O T0.
Aí depois, mas aí o T1 não está bem definido.
Exato.
Aqui, so in this other graph, we don't have that problem. Here what we can always do is just forget about this point, no? Now we have another graph which is nice, and we can define the random walk here. And we can also define the random walk here, right? Notice that this random walk here has some property which many times is not very pleasant. It's not very nice, which is the following. So there is a parity conservation in this random walk. So if you start here, at even times you're always here or here, and at odd times you're always here or here. No? So in t equals 126, we know that we are going to be at one of these 2 points. Which one? Well, there are some probabilities to be computed, but certainly on one of these 2 points. And at t equals to 225, we know that we are going to be at one of these 2 points. Which one? Well, there are some probabilities to be computed, but so it's not nice in the sense that there is still some predictability about the motion of this random walk. Here you don't have that problem, no, because of this triangle here, you don't have that problem anymore. So So this is it's not yet a rigorous definition of a random walk. So if one wants to start to define, okay, so I can anticipate that a random walk, it's a particular case of a Markov chain, okay? Sometimes, no, there are some things that you can compute. For example, in the complete graph, one can make some computation, no? So let's do some computations just to start to learn how to do computations, no? So let's do as an example the complete graph. So if you start at a point, a given point, so let's take x on V, which is just the set. Okay. So the probability. And let's take x0 equals to x. Okay. So now let's compute the probability of x1 b equals to y, where y is some point on the complete graph. So there are two cases. So it's either equals to 1 over n minus 1 if y is different from x, and 0 if y is equal to x. Right? Because you can go to any other point uniformly at random, but you cannot stay at x because I didn't put the loops. Differently would have been if I also put the loops on the complete graph. Okay?
But that was 1 of the degree.
Huh?
1 sobre o grau, sim.
1 sobre o grau. So now let's compute what is the probability of x2 being equal to y. There are also two cases. Whether y is different for x or equal to x. So let's see what is the probability of being at x after two steps. So you are somewhere in the complete graph which is not x, and now you have to choose x. But independently of where you are, the chance that you are going to choose x in the second round is 1 over n minus 1. So this is always 1 over n minus 1. And here, well, here I can cheat a little bit, and I can use that probabilities has to add up to 1. Instead of doing the computation, I can just write down directly this number here. Right? Because the sum has to be equal to 1. There are n minus 1 points of this type here. So the total probability will be n divided by n minus 1 plus 1 minus n over n minus 1, 1. I'm correct or not? Maybe I'm doing a mistake. Yeah, I'm doing a mistake, so it's n minus 2 here. Okay, so now you can keep going, no? So exercise. ¿Sí? ¿Ah? Sí. Y dividiendo por n-1 porque hay n-1 de estos. Exercise. Keep going. That is, compute the probability of xn, well, maybe not t, equals to y for all t bigger or equal than 3. Okay? So you can compute it. It's not very difficult, no? There is some recursion to be solved, though. This is not, I'm not going to do it now. But as I was telling you last time, it will be nice to try to build up a methodology to do these computations, because they are not super fun to do. So we're going to make a definition. So stochastic matrix is a square matrix, okay, of this form here, such that all the entries are non-negative, and the sum of the entries at each row is equal to 1. Okay? So, quick observation here. Usually when we talk about matrices, the indices are not on a set V. No? The indices go from 1 to n, where n is the size of the matrix. Right? But since V, it's when V is finite, you can just label the set V from 1 to n, and then you get a matrix here, a stochastic matrix, in the usual sense. But there is something more general here, because this also includes the case on which V is infinite. So when V is infinite, this matrix here is actually an infinite matrix. Okay? So if you never encountered an infinite matrix before, there are some few things that one has to be worried about. Is that when you have an infinite matrix, so infinite matrices, the operation of infinite matrices is the same as finite matrices. You can multiply them, you can add them, etc. But there is a catch, and the catch is that, for example, when you multiply two infinite matrices, in order to compute one entry of the product, you have to do an infinite sum. And whenever you do an infinite sum, you have to check whether the sum is well defined. Okay, so sometimes it's annoying because infinite sums has to be absolutely summable. Otherwise, the order of summation could affect the result. Okay, but for stochastic matrices, we are okay because of these two conditions. So you can always multiply stochastic matrices, because the entries are always non-negative, and the sum is, they add up to 1. Okay, so the usual algebra structure of matrices is also preserved in the world of stochastic matrices, even when the vertex set is infinite. Okay, so this is an stochastic matrix. So now my goal is to give a rigorous definition of what we call a Markov chain, okay? And in particular of a simple symmetric random walk. So I had to make another definition. So a definition okay. Okay, so I had to introduce the concept of a stochastic process. Okay, so a stochastic process is just a fancy name for sequence of random variables. Okay, so each one of these guys is a random variable, and now you have a sequence. And instead of calling sequence of random variables this type of objects, we used to call it a stochastic process. Okay, so this is something that for some reason people do in mathematics in general, is that they invent new names for things that are already defined in some other context. Okay, so you may have found that, no, that for example, so in dynamical systems they have this fancy name, no, dynamical system for a function, no. So what is the dynamical function? And well, that's one example. In probability, this is another one. So what is a stochastic process? Well, a sequence. And so you don't have to be scared about this name, stochastic process, because sometimes people are very scared about these fancy names. Dynamical system, yeah, dynamical system. Stochastic process. Whoa. I don't have any idea.
Good one.
Acho que vem de estoque mesmo.
Ou será o contrário?
O estoque vem disso. Acho que vem de estoque, eu já vi uma coisa sobre isso.
Acho que uma parada que em relação a uma outra variável de grandeza pode ser tempo,
O estoque no
grandeza.
sentido de você estocar.
Estocástico não é porque ele vem de passos. 1, 2, 3, 4, 5. Porque por definição, processo estocástico ele é algo que tem uma sequência, né? Pode ser tempo, pode ser grandeza, pode ser espaço.
Não sei. Então, eu acho que essas perguntas caem na categoria de é ou zero um número natural? So now, okay, let me see. I'm going to
Destacar significar o que pode ser previsto.
Bom, excelente. Ok.
Bom, me parece o contrário, né? Parece algo que é aleatório, não pode.
Não, senão a gente não teria as áreas de sexta colagem, previsão, mais
Bom, se serve de algo, serve de onde vem random. Do francês. Então, em francês, so in French, there is a verb, randonner, which means to wander, ou seja, vagar pelo mundo, contemplando os arredores do universo.
Vem do grego, da palavra stokos, que significa alvomenta, mas a palavra vem de outra palavra que é derivada dessa, que é estocásticos, que pode significar fazer suposições. Pelo menos é o que a internet disse.
You know, so there is this story about the name random variable. So when these guys were inventing probability theory in the beginning of in the first half of the 20th century. No, well, yes, after Kolmogorov. So there was, I think, Feller and Chung.
Feller.
Yeah. Who were the guys that were starting to write books about it. So they started to teach others about probability. So I think one of them wanted to call random variable, and the other one wants to call it chance variable.
Chance.
Yeah. So how do we decide? So they decided to toss a coin.
It is a fancy name for a function too, right?
Huh?
It is a fancy name for a function.
So let me do a definition. So let omega be a non-empty finite or countable so this is going to be called state space. So state space is also a fancy name for set, no? Let P be a stochastic matrix. And let mu be a probability measure on omega. we say that stochastic process xn such that n is n0 so this is something, so here I made a small mistake. So this is something that one student once taught to me. When you write a sequence and you put these ones here, it means that the order of the terms of the sequence doesn't matter. And when you put these ones here, it means that the order of the terms of the sequence matter. So here the order is important because it's one can see it as the flow of time. Here the order doesn't really matter because these numbers here are not really ordered. So you put these ones here. Okay, so anyway, so let's go with the definition. So since this is the most important definition of the course, I'm taking my time to do it very, very, very precise. Okay? Process is Markov chain of state space omega transition matrix P and initial law mu if for every t bigger or equal than 0 and every sequence x0, x1, xt in omega such that every such that so this one is the probability of x0 equals x0, xt equals little xt bigger than 0. Every y in x probability of x t plus 1 equals y given is equal to p Okay, so quick announcement about notation. Okay, so here I wrote the matrix as P subindex ij, and here I write in the matrix as P, but not with subindices, but with the arguments. Okay, so this is something I'm going to do very often, is that I'm going to switch from subindices to arguments in the notation whenever it's convenient. So here it was convenient to put the subindices because this is the usual notation for matrices. If I put these guys as subindices here, the guys at the back won't see anything. Also, the people at YouTube won't be able to see a thing. Okay, so this is just a quick announcement about notation, that this P here is the same P as here. Okay. So this is the definition. It's a very long definition. And so whenever you do a definition in mathematics, the first things that you have to do is to check whether your definition makes sense. Okay? So this is a conditional probability. How is defined? So let me just remind you about conditional probability. The conditional probability of an event A given another event B. So event, one more fancy name for set. So the probability of an event A given an event B is the probability of the intersection divided by the probability of the second event. So this is the definition of conditional probability. Right? So this condition here is there only to make this conditional probability well defined. Okay? Another thing which is important, here if you add over all points y on the set omega, you should get 1. Because the probability, the conditional probability of this guy being somewhere is 1. Because it has to be somewhere. So the sum on the left-hand side is equal to 1 when you sum over y. On the right-hand side, the sum here is the sum over a row of the matrix P. So this is why we're asking the matrix P here to be a stochastic matrix. Okay? So this is, in principle, this is well defined. Okay? Whether it makes sense is another question. Okay? Yeah? Ah, yes, I forgot. That's the second thing. And for every, this is why one always has to check whether a definition makes sense. So what I'm saying is that the initial law of this stochastic process, of this sequence, is the measure mu. Okay? Quick observation. So maybe it depends on where did you, with bibliography you use to learn probability theory. They use the word distribution instead of law. Okay, they'll talk about the distribution of a random variable. I tend to use the law of a random variable because for me distribution is another thing. Distribution is a tempered distribution. Is what people use in PDE. So my line of work is it's a stochastic PDE, which means that I had to work with distributions in the PDE sense and distributions in the probability sense at the same time. So it's very convenient to have a different word for two things that are different. So I'm very used to I'm very used to use always law instead of distribution because of that. Okay. So in case you were wondering whether law and distribution is the same, it's the same. Não é densidade porque nem toda a probabilidade tem densidade. Não, não é um traço mostral. Sim, não. O espaço mostral está lá em algum lugar. O ômega...
Apesar da soma dele ser 1, não significa que...
So this is the definition. And so this is the definition of Markov chain, okay? And the first, so let's just quickly prove something that I'm going to call a theorem. It's actually a very simple observation, but I'm going to call it a theorem, and I'm going to also give it a name, the chain theorem. Okay, because since you were asking about names, why Markov chain? Well, Markov because of Markov, the mathematician who introduced the concept, and chain because of the chain theorem. So what is the chain theorem? The chain theorem says that, so I'm not going to repeat the hypothesis of the theorem because it's too much. But under the same hypothesis, what we have is that the probability of f0 equals to little x, x1 equals to little x1, xt equals to little xt, it's equal to mu of x0 times the product from I equals 1 to t of p of I minus 1 xi. Okay, so if you want to compute what is the probability to see one particular trajectory of a Markov chain, the answer is, well, first you have to see the right initial condition, and then you have to multiply the probabilities of seeing the right jumps of the trajectory. Okay? So I call this the chain theorem because this is like a chain, no? These are the slabs of the chain. This is the anchor point. So you have a chain, an anchor point. So this is a graphical representation of that formula there. Right? So where this guy here represents the points little xi, and each one of the slabs is this probability here. So the let's put one more. So the proof is very easy, no? It's just recursively use this definition here. So I'm not going to write the whole proof. I'm just going to show you how to start the proof. Okay? Huh? So we just have to use this formula the other way around, no? So we have to express the probability of the intersection as a conditional probability times the probability on the denominator. So by the definition of Markov chain, the first probability is equal to the corresponding entry on the transition matrix. And the idea is that once one has this formula, one can use induction to prove the theorem. Right? Because I expressed the probability of the case. So maybe, well, it doesn't matter. No, the case of case t in terms of the case t minus 1. So that's the induction hypothesis. And then you have to verify that the formula is correct for t equals 1. And when you verify the formula for t equals 1 is where the mu of x0 enters into the computation. Okay? So this is the chain formula. That explains the name Markov chain for a Markov chain. So now we can define in a more rigorous way what we understand by the simple symmetric random walk. Okay, so I'm going to write that as an example. A simple symmetric random walk. So this is the usual notation people use on a graph G. What it is? So is a Markov chain. So as you can see, okay, so on a graph G, starting at x0 on V is a Markov chain. Okay. So a Markov chain depends on 3 parameters, right? The state space omega, the transition probability p, and the initial law mu. So whenever you say that something is a Markov chain, you have to specify these 3 parameters. Okay? You have to pay attention to that because usually in the literature, people say, this is a Markov chain, and that's it. Okay, so they don't specify the parameters because they are understood from context. This is very usual in mathematics, but when you do it for the first time, you have to be very picky about defining everything very precisely. So this is like this is the lesson of my professor of jazz. Okay, so at some point I decided to do music because this math business is too boring. So I went to study music, and I had the professor of jazz. So he was telling me, no, because people want to learn to improvise, to play out of the box. And what is very difficult is to make these people understand that before learning to improvise, you have to learn to not improvise, to be in the box. So this is also true for mathematics. So before going out of the box, and you have to learn to be very precise. Before starting to be imprecise, no? And to say, no, this is understood from context, you have to learn to be very precise. So this is what we are what we are doing now. Hopefully, after a few lectures, we can start to be more relaxed on formality. So whenever you say that something is a Markov chain, you have to specify these three parameters, no? The state space, the transition probability, and the initial law. So it's a Markov chain with the state space. So the state space is V, no? So of all these among all these definitions, when you do this is the most important, no? The core of the Markov chain is the transition matrix, because that's what tells you how the dynamics actually is. So this is the matrix P. So it's 1 over the degree if the destination point is connected to the starting point, and it's 0 otherwise. So here, delta x0 denotes the singleton at x0, meaning the measure that puts total measure at x0. So it's the measure mu that is equal to 1 at x0 and equal to 0 everywhere else. Okay? So this is effectively a simple symmetric random walk is a Markov chain. So, okay, so the definition is okay. Then we have at least one example. So a mathematician will be always picky at this point about something else. There is something we haven't said yet, is whether Markov chains actually exist. Okay. So there is a theorem. And it's called the Kolmogorov consistency theorem. Recently, another student of mine, so this is good at IMPA because you have lots of very good students that are constantly teaching you something new. So there is a theorem that I didn't know. Let me see. Perfeito. Ah, tá aqui, exatamente. Então, esse teorema aqui é o teorema. Okay, so this theorem here is the Kolmogorov consistency theorem. So the general, so the Kolmogorov consistency theorem is more general, but the particular case that we are going to use for Markov chains is actually called the Ionescu Tulshea theorem. So what this theorem says, okay, so maybe I'm going to write it up here because I'm running out of space there. There exists a stochastic process satisfying the chain formula. This law is uniquely determined by that formula. Okay, so I'm not going to prove this theorem because it requires some measure theory, and it's also not needed anymore for the course. Okay, so the Kolmogorov consistent theory also, or also the Ionescu-Tulshea theorem, tells us that there is only one process satisfying this condition. Okay. In the sense of the law, because there could be two of them, because you have different probability spaces. Maybe you can construct two different stochastic processes in two different probability spaces, and both are Markov chains with the same parameters. But they have to have the same law. Okay, so that's everything for today. So João Pedro is there to tell you about the